Yes, good morning, good morning, good morning. Good morning. So all fine? Yes. Good morning. Yes, all good. Okay. So yes, good morning. So in last class, what was the topic we have completed? Yes, good morning. In last class, what we have done? Yes. In calorimetry, how many questions? Phase change. So questions on phase change and temperature change. Okay. And how many questions we did? Phase change and temperature change combinedly we have done some questions. Phase change and temperature change combinedly some questions we have done. In which phase change and temperature change? Like questions like this. Yes. How many questions we did combinedly? Like ice to water, ice to steam, these type of questions. Ice to steam, ice to water type questions. 5 questions. And we did energy absorbed as well as released also. I think at the end we did one question on the energy released. Energy released, that question was also done. Energy released, that was also done, na? Yes, okay, yes, good morning, good morning, good morning. Yes, that question also done. So now, today we have to do some more questions and mainly mixing. I think I said in the last class that next we are going to start mixing. Yes, I said this thing that we'll be starting the mixing. Yes. Okay. So before mixing, I'm going to give you one question. Let's see how many people are able to solve this one. Okay. Before mixing, giving one question. Heat capacity also we have written. Heat capacity. Heat capacity written. Heat capacity was over. Heat capacity. No. No. Okay. The heat capacity, no. Okay. Water equivalent. So water heat capacity, no. Water equivalent also, no. Okay. So these things we'll write first. Okay. So let's write heat capacity first. Okay. Listen. Heat capacity is nothing. Most of the time, what we have to do basically, they have to give mass as well as specific heat. Both the things should be given to us. Whenever you have to calculate the heat will be basically ms delta theta. So for the calculation of heat, we need mass also as well as specific heat. So they will not give you mass and specific heat separately. They will give you both in the combined form. Both in the combined form is known as your heat capacity. Means we can say heat capacity nothing but the product of M and S. M and S combinedly known as heat capacity. So this is nothing new. Combinedly, these are known as heat capacity here. Now you know Q is basically ms delta theta. So in terms of heat capacity, I can write this one Q equal to ms is basically your heat capacity. So you can say this one can be written H. Okay. We can write heat capacity into delta theta. Okay, so Q equal to ms delta theta, and we can write here in this one ms is basically your hc, so it becomes your hc delta theta here. Okay, now we can see this is heat capacity is actually equal to ms. Okay, that's why this Q sometimes I can use, most of the time I'm going to use ms delta theta. Sometimes in place of ms I can put hc, so Q becomes hc delta theta. Later on somewhere we'll use. And then we can get H equal to ms. M is basically volume into density. Okay, this is the volume into density. So we can say this becomes V rho S. Okay, so sometimes I can use this thing also, that heat capacity equal to V rho S. Okay, V rho S. Now they will ask a ratio of the. Okay, like if I ask one simple question, if I ask here in this one, they will say that we got, okay, mass H, okay, mass they have given in this one, like this is given, okay, suppose 2 kg, okay, 0.2 kg, okay, or I can take, suppose they have given mass as, okay, 20 gram, and specific heat they have given here in this one, okay, suppose this is given here in this one, 0.2 calorie per gram degree Celsius. They are asking specific heat, means heat capacity in joule. Heat capacity in joule they are asking, okay? Heat capacity they are asking in the joule, okay? What you can do if you want heat capacity in the joule, okay? So first we can find in the calorie only. So we can say heat capacity becomes here M into S. So you can say 20 into 0.2, which becomes how much? 20 into 0.2, you can see, sir, this becomes 4 calorie, okay, 4 calorie per degree Celsius, because gram will be cancelled, okay. If you say, then gram and this gram will be cancelled, so 4 calorie per degree Celsius. Anyone is asking unit also, na? So you can say unit will be here, okay. Unit will be joule per kg, no, not kg, joule per, okay, Kelvin, or we can say calorie per degree Celsius. This is the unit for this one, okay. Now they are not asking in the calorie, they are asking in the joules. Sir, this week exam is not there. Probably it may not be there because syllabus is very less. Okay, and if syllabus is less, then there is no point of examination because we have to frame 50 questions. Okay, so at least there should be enough content to frame 50 questions. Okay. So now we can say an exam is there or not there, you don't have to worry about the examination. All the time you need, okay, you should be prepared that whatever is completed, I am perfect in this. Whatever completed, I am perfect. Okay, whatever the syllabus doesn't matter. Whatever completed, I am perfect. Because paper will be coming, whatever things are completed, from there only paper will come. Okay. So now we can see 4 calorie is basically 4.2 joule per degree Celsius. So it becomes actually here 16.8 joule per degree Celsius. Okay. So they can ask like this question. This is a very basic question here. Just we have multiplied M and S. Okay. And then they're asking in the joules. So we have written 1 calorie is actually 4.2 joules. So, okay, calculated here. Okay. Now we have next thing in this one. They are asking in this. Sometimes they will ask question on the ratio. Okay, so they can say ratio of the heat capacity HC1 by HC2. So you can say HC1 by HC2 if they are asking. Then we can say, sir, this will be the same M1S1 by M2S2. So we can say it becomes M1S1 by M2S2. Some of the people can say we can write like this also, V1 rho 1 S1 divided by V2 rho 2 S2. If I say here, if material is same, then you can say, sir, if material is same, okay, if they have given anywhere, sir, material same, then you know, for the same material, which parameter will be same? Of course, mass will not be same. Mass can be different for the different material, but their properties and whatever the parameter depends on the properties, like specific heat depends on the property. Density is the property of material. So we can say specific heat as well as density is going to be constant. So rho and S will be same. And if rho and S will be same, so we can say HC1 divided by HC2 here becomes actually your V1 by V2. Okay, HC1 by HC2 becomes V1 by V2. Now we can say they will give you sometimes a spherical body or any body is given, like if they have given the cube also. For the cube also, you know, volume is proportional to A cube, and for the sphere we know volume is proportional to R cube. Okay, so any body is given, we can find ratio of volume. I am writing for the sphere. If spherical object given, then we can say for the spherical object we can write volume proportional to R cube. So we can say HC1 divided by HC2 finally will be equal to, in this one, your R1 by R2 whole cube. I hope this one is clear. Yes, HC1 by HC2 equal to R1 by R2 whole cube. Clear? Can we do questions on this? Some of the questions on this topic. One question already, okay, already we have done. There was the just multiplication of mass and specific heat, but unit conversion was there. We need to do the unit conversion. Sometimes in the unit conversion only, okay, they play and we trap. Okay. So, right, next question here. So I will give you radius. If I give you radius, you can easily figure out your ratio of heat capacity. And once you are able to find your heat capacity, then we can find, they can ask heat capacity also, or they can ask amount of, okay, they can ask amount of heat required also. So we can find anything. So in the next page, I'm going to write one question on this. If you have any problem here, you can ask freely. Yes, anywhere, any problem. No problem. Okay. So question is, find ratio of, okay, heat required to reach temperature by 1 degree Celsius for two spheres with radius R and 1.5 R. Okay, they have given find heat required to raise temperature 1 degree by 1 degree Celsius, and radius is given R and 1.5 R. So now we can see here in this one, Q1 by Q2 will be actually equal to, here in this one, HC1 delta theta, because I have told you Q is ms delta theta, and in place of ms I am putting here HC. Okay, in place of okay, ms I am putting HC, so we get HC1 delta theta by HC2 delta theta. Delta theta will be cancelled. So you can say Q1 by Q2 is actually nothing but the HC1 by HC2. It is the nothing but the HC1 by HC2. Okay. And now HC1 by HC2 you have to find, and you know in the previous slide, if you remember, that HC1 by HC2 was told to you R1 by R2 whole cube, R1 by R2 whole cube. So now we can write here in this one, HC1 by HC2, okay, is nothing but R1 by R2 whole cube for the spherical body. I hope, okay, we are getting this point. It was written here that HC1 by HC2 is V1 by V2, which was equal to R1 by R2 whole cube. So I got this thing, and this Q was basically ms delta theta. In place of ms, HC was written. That's why Q equal to HC delta theta. Now we can say Q1 by Q2 actually becomes here in this one. R1 is your R, R2 is 3R by 2, so it will be going upside into cube. Now R cancels, so 2 cube is 8 and 3 cube is 27. That is the answer here. Okay. Yes. Next question now. Necessary to read and listen. NCRT we have to do in full physics. NCRT we have to do in full physics, okay, but not reading actually. Means if you get that, because you will not get time for the reading. So solved example we have to do for complete, okay. You may not get time to read NCRT in physics, okay, but at least we have to do solved examples we can do, okay, in the NCRT. And at the last they have written somewhere points to ponder, and okay, that part we can do, okay, but there is no much time for us to do a lot of things, okay, so reading may not be possible, okay. In this one, what I am saying here, Q is basically equal to here, you know, ms delta theta, okay, Q is ms delta theta. Arsad, listen here. So I'm asking ratio of heat required, means ratio of Q I'm asking. So you can say, sir, Q ratio means we have to find the actually Q1 by Q2, and I can write this ms as HC, because you know heat capacity is the ms. So this can be written as HC into delta theta here, and then we can say Q1 by Q2 actually becomes, okay, HC1 divided by HC2, and delta theta is same because 1 degree Celsius. So delta theta is cancelled here, okay. So Q1 by Q2 becomes HC1 by HC2, and then we can write here HC1 by HC2, okay, in the previous one told R1 by R2 whole cube here, okay. So we got answer R1, I can put R, and they have given 1.5 R. 1.5 R is basically equal to 3r by 2, because I said already we will prefer calculation in the fraction rather than decimal. Okay, so this is the things written here, 3r by 2, and then okay, r are cancelled. I hope you got the question. Yes. Now we are moving forward here, okay, and we need to, yes. So right, next one here, water equivalent. Okay, now notes enough to refer. No, module you have to always you have to do. Okay, notes along with the module we have to do the practice. Without okay practice, things will not come. So module we have to do, and NCERT solved example we have to do. Okay, exercise 130 marks, exercise 230 marks, exercise 330 marks. Okay, very popular formula is there. Okay, in this one, okay, exercise 1 if you do 30 marks, exercise 2 30 marks, exercise 3 30 marks. Okay, solved example 30 marks, focus 30 marks. Okay, notes 20 marks, NCERT things. Okay, we can say remaining. Like this, if you do all, then only it becomes your okay 200. Okay, then it becomes 200. So if you're thinking that only I will do notes, it may not be enough. You may get just okay 40-50 marks. If you're saying this, I will do exercise 1 and notes. Okay, then you can get somewhere around 60-70 marks. So you need to do all the things as much as you can. Okay. Of course, we cannot go beyond our limitation, whatever, okay, your capabilities are there. You cannot stretch too much. You cannot give stress to your body and brain. But whatever max to max we can do, that we have to do, okay? And that will be proportional to your marks all the time, okay? So maximum efforts you have to, okay, do, okay? I'm not saying that each time you have to do the exercise 3, okay? Sometimes what will happen that you will not be having time, okay? Time will not be there to do. So no problem. Whatever you can do, but make the rule that exercise 1 and exercise 2 I will do mandatorily. Okay, make this rule in your life that exercise 1, exercise 2, and solved example I will try to finish. At least bare minimum is this thing. And solved example also that okay, if it is too lengthy, you can ignore. If okay, small solved example we can do. So make this bare minimum. We have to do this much for the selection. If you do some more, then okay, you will get more marks. But for the selection, bare minimum is this. Yes, from there only you can do. Okay, it will be there in the app. You can okay find all the things you can do. Okay, practice is required actually. Okay, suppose gym solved example I am saying, as well as NCERT solved example also. Okay, without practice things will, like you are going to okay for boxing, okay, and if you are going for the boxing, okay, boxing preparation, so for the boxing you okay, you are watching so many videos, you are reading so many books, okay, you want to learn the boxing, and for the boxing, okay, daily I am coming in the YouTube and teaching, yes, like this and like this, okay, and then you got, yes, this way I can punch, okay, so you're daily watching the videos, okay, and daily reading the books that yes, if okay, this will be the attack, this will be the defense, okay, and all the things you are, so theoretically you are perfect, but when you will be inside the ring, at that time you will be able to defend. When you will be inside the ring and you will be like this, in the ring you may not last for okay 5 minutes also. Why? Because you never practice that. So what is required actually? We need to watch the strategy. Okay, strategy, okay, teacher will tell, yes, like this, okay. You are reading theoretically, yes, we know, and then we need to do practice. So practice is actually very, very important all the time, okay. So make this rule that daily you have to do practice. Some questions at least how to do. Okay, and exercise 1, exercise 2, I will never skip in any chapter. In any chapter, I am not going to skip exercise 1 and exercise 2. Selection will be there. And Generally what happens, people skip the exercise, they just do the notes, okay? They get the marks, but ultimately I said now without okay, practice things will not be perfect, okay? So some practice is all the time required. So now we are ready here. Next, water equivalent in this one. So listen, water equivalent right now, okay, I will just tell the meaning of this thing. I'm not going to explain here, okay, because we have to do a lot of questions today. Later on, if you want, you can ask the definitions, or definition you can read from anywhere, okay? So water equivalent means, I will write with the W, okay? Right? It is numerically equal to heat capacity. Water equivalent is numerically equal to heat capacity. Numerically equal to heat capacity. For us, this is the meaning of water equivalent. I am not telling the definition. Okay, it will take around 5 minutes or 10 minutes around. Okay, it will take. So just meaning, I am saying what the meaning for us. Water equivalent nothing but the heat capacity. That's it. Water equivalent is nothing but the heat capacity, numerically equal to heat capacity. It is numerically equal to heat capacity. It is numerically equal to heat capacity, okay? Means whenever they have given the water equivalent, you will treat as heat capacity is given. Sometimes they will not give you the heat capacity. Heat capacity word will not be given. They will say water equivalent, means we can say there is the heat capacity given already, okay? So for you, heat capacity, water equivalent, similar, okay? Yes? Now, how to do means suppose like if I say question here, okay, they will say if water equivalent equal to 20 gram. Water equivalent is actually mass of water, okay, mass of water which is equivalent to that material, okay. In short, if I say mass of water which is equivalent to that material, exact definition I am not telling right now. So if water equivalent is 20 gram, then heat capacity we can just take the numeric value. So it is the your 20, okay, it is the 20. Clear? Water equivalent is 20 grams, so heat capacity is how much? Your 20. And this will be basically the calorie per degree Celsius, okay? Because whole calculation here we are doing in the calorie or joule, in the calorimetry, okay? Name itself, name of the chapter is the calorimetry, means we are doing most of the things in the calorie. If they are asking in the joule, we can convert later on, but calculation we are doing in the calorie, okay? Sometimes what will happen that water equivalent they will give you in kg, like 0.3 kg, okay? So we can say this kg should be converted to gram, because we are doing all the things in the calorie per gram. And you know, water specific heat, when I will prove this, or if I go for the definition of this one, water specific heat is 1 calorie per gram, okay? So we need to convert into grams, so this becomes basically here 300, okay, gram. Then I can say heat capacity, which is the ms, will be equal to 300, okay? 300 will be in the calorie per degree Celsius. So if it is given in the gram, there is no problem, there is no issue at all. If it is given in the kg, then you have to convert into gram, okay? If it is given in the kg, we have to convert into gram, okay? If it is given in the kg, then you have to convert into gram. That's it. Okay, and the numeric value in the gram, whatever the value is coming in the gram, that numeric value is equal to ms, or that your heat capacity. Can we write some questions on this thing? Actually, if you have to heat the ice, or you are going to heat water, okay, either ice or water, can I put directly ice or water on flame like this? Can I put on the flame? No, not like this, okay? Game of flame will be over. Actually, we need some container. I need to have some container. In the container, I will put some ice or water or whatever, okay? Then I can heat, okay? And in this process, you will say, sir, who will take the energy first? Ice or water, or container is going to take the energy first? Here container absorbs energy first, and container transfer this energy to the ice or water. So here, okay, first recipient of energy. Who is going to receive the energy first? Container. And where container is receiving the energy, so temperature of container will not be constant. Temperature of container will also increase. Temperature of container will also increase. Yes? Temperature of container will increase, na? Means if temperature of container is increasing, it means if temperature is increasing, it means we need to consider energy taken by the container. We have to calculate energy absorbed by the container. In the previous question till now, whatever we have done in the last class, we never considered the container because I didn't give the container parameters. If they have given the container parameter, what are the container parameter? Mass given, specific heat given, then only you can calculate the heat required, okay? Because container temperature will be changing from theta1 to theta2, means we can say ms delta theta. So ultimately we need mass as well as specific heat, or we can say we need heat capacity combinedly as ms, or we need basically your water equivalent here. So if they have given the parameter of the container, you need to always consider energy absorbed by the container. If they have not given the parameter, of course will not take, like till now we have never considered. Now we are going to take if they have given. So when question will write, and that container in which we are doing this thing is known as calorimeter. In this chapter, that container in which we will be doing the mixing related things is known as calorimeter. So we'll write one question here. A calorimeter contains 20 gram ice. A calorimeter, and here we can write in the, okay, here a calorimeter of water equivalent okay 15 gram, or better I can say okay, so this is given a calorimeter of water equivalent 15 gram, okay, 15 gram contains 20 gram ice at 0 degrees Celsius. Find heat required to convert into water at 40 degrees Celsius. This is the question, okay. In this question, they have given parameter of the container. Earlier, what we were doing, we were only considering the ice, like this was the ice here. This was 0 degrees Celsius and 20 gram. So we were writing, sir, ice will be going to water 0, and then water 0 will be converted to water 40. And this energy, when we are writing, it becomes basically here MLF, and this is the MS delta theta. Here we can say M is 20, so we can say 20 into 80, that is the 1600 here. And here we can see it is the 20 into 1 into 40, that becomes 800 here. So if I say total, we say here energy for ice, energy required for the ice. So energy required for the ice is this, okay. But container is also given, and we know container also will take the energy. This is the calorimeter, and its water equivalent is given. Water equivalent means always MS is given. That is the 15. This is at 0, this will be also at 0 degrees Celsius, okay. Its initial temperature, of course, will be same. They will say temperature of ice means that will be the same of for container. And finally, water is 40, so container will be also reaching to 40 degrees Celsius. How much energy container will absorb? We can say MS delta theta. So we can say MS is 15, delta theta is 40. So 600 additional energy is taken by the container. If you have to answer total, then we can write total energy required will be, in this case, this plus this plus this. That actually becomes 3000 calorie, okay. Now, in this question, if I don't give you, okay, if I don't give container parameter, if parameters of container not given, they are saying calorimeter, but they have not given parameters, means they have not given values for the container. Water equivalent not given, specific heat not given, heat capacity not given, then what will be the answer? If they are not given, okay, heat capacity and all these things for the container, then what will be the answer? In that case, our answer will be, yes, in that case answer will be this plus this, means 2400 will be the answer, okay. If they have not given anything for the container, our answer will be 2400. And if they have given parameters, our answer is going to be 24 plus 6, that actually becomes 3000, okay. Yes. Can we go for next thing? Okay. So next concept I will how to give one question to you and you have to solve. If I say vaporization will start, okay, vaporization will start at the 100 degrees Celsius or before 100 degrees Celsius? Vaporization will start at the 100 or before 100? What do you say? Vaporization will start at 100 or before 100? At 100, before 100 vaporization will not start at all, okay? Before 100 vaporization will not start at all, okay? Yes? Huh. And melting will start at what temperature melting will start? Melting will start at 0 degrees Celsius, okay? Means if ice is not at 0, melting will not start. To start melting, ice must be at the 0. Ice must be at 0, then only melting will start. Otherwise, melting will not start. Ice must be at 0. Then only we can talk about melting. Till ice is not coming at 0, you can never say that melt. Okay, ice will be ready to melt at the 0 degrees Celsius. Okay, ice will be ready to melt at the 0 degrees Celsius. Okay, if you say that ice is suppose at the minus 10 degrees Celsius, if you say melt, it will melt. Suppose ice is at minus 20 degrees Celsius and you say ice melt, it will melt? No, it will say first give me some energy so that, okay, I go to 0 degrees Celsius and after that you can melt as much you want, okay? Means suppose this block of ice you are having, if this is the block of ice and okay, you are saying that, okay, just I want a little bit melting. It will say this melting, okay, no problem. But first you have to convert this whole block to 0 degrees Celsius. First, okay, take me to 0 degrees Celsius. After that, you can melt whatever you want. You can melt 1 gram, you can melt 2 gram, you can melt 3 gram, you can melt 4 gram. Whatever gram you want, you can melt. But first, you have to bring me, okay, you have to keep me at 0 degree Celsius. Then only I will be ready to melt. Otherwise, I will not melt. Okay, this is the condition for the ice. Ice cannot melt at the minus 40 degrees Celsius. Ice cannot melt at the minus 5 degrees Celsius. Ice cannot melt at the minus 10 degrees Celsius. Ice will be ready to melt at the 0 degree Celsius. Okay. I hope this thing is coming here. Ice will be ready to melt at the 0. First, we need to bring that ice to 0 degrees Celsius. Then now it will be ready to melt. Okay. So now we can say one question is here. Right. You have m gram ice at minus 5 degrees Celsius, okay, minus 5 degrees Celsius. When 1680 joule, you know that 1680 joule is given, but okay, we have to consider all the time in the calorie. 1680 joule energy supplied, then 3 gram ice melt. Okay, only 3 gram melt, not the total m gram. Okay, only 3 gram ice is melting when you are supplying this much energy, not full ice. Okay, only 3 gram. Find m. Find m. Okay, what are the m actually you have to find here? Okay, you can say, sir, q first of all I can write the 1680 joule. I have to write in the calories. So 1680 divided by 4.2, and this actually becomes how much? Your 400 calorie, because this much energy I have given here. Okay, this much energy was given. Will you try this question? Will you try? Let's see how many people are going to get correct answer in this question. Because concept already I said, melting will be only melting will start only at the 0 degrees Celsius. Before that, melting will not start. Okay, so let's see how many people are going to get correct answer here. Make it fast. Do it fast. I am you have to find, okay, And here energy is given. In the previous question, mass was given. So we were finding the energy. Here energy is given and you have to find the mass. Okay. Let's see who is getting the correct answer. Don't Google, okay? Because Google you will not get the answer. Whatever question I am writing here means, okay, you will not get in the Google also. So Google will not work. You have to solve. 163 gram Amrut Anand, answer wrong. We received first answer, that was wrong. Amrut Anand, 163 gram. Next one. Try, okay, at least you tried, that is a good thing, okay? Still some people are not, they are not attempting also. Okay, so this side we got Visesya got the correct answer. Answer I will not tell, but Visesya got correct answer. Lakshmi also got correct answer here. And hi, hello also got correct answer. Okay, so many people are now getting the correct answer. Okay, listen, we will do this one. We can say we have here m gram ice. This is the ice basically here. Okay, this is the m gram and it is a minus 5 degrees Celsius. Okay, you know that the ice will be ready to melt. Okay, but first this whole block you have to bring. Okay, you have to keep this whole block to 0 degrees Celsius. Then only ice is going to melt. Otherwise, ice will not melt. This whole thing you have to keep at the 0 degrees Celsius. Okay. After that, you can melt as much you want. Okay. You can melt 1 gram, 2 gram, 3 gram. So this whole thing, how to come at the 0 degrees Celsius, is this whole m gram will be coming to 0. In this process, some energy will be used. Okay. When you are bringing this one to the 0 degrees Celsius, some energy will be used. Okay. How much energy will be used? We can say ms delta theta. M is ms, of course, ice, so half. Delta theta will be 5. So this much energy is only used to bring this ice to 0 degrees Celsius. Means it's still melting. Okay, now melting will be, okay, now it is ready for the melting. Now melting will start. Before that, there was no melting. It is coming to 0. This energy just used to bring this ice to 0 degrees Celsius. Now it will say, yes, now you can melt whatever you want. Okay, now we can say how much ice melting here. 3 gram ice melt. Okay, so we can say in the this energy was consumed just to bring to the 0 degrees Celsius and 3 gram ice melt. So we can write here in this one. For this one, it will be the MLF. So we can say 3 into 80. Okay, 240 calorie. 240 calories used for melting of 3 gram, because they have given only 3 gram is melting. So for the melting of 3 gram, how much energy is consumed? 240. But before this, you don't have to bring 3 gram. You have to bring whole m gram. Complete m gram will be coming to the 0, then only it is ready to melt. So we can say this energy plus this energy, the absorbed energy, it should be equal to given energy. So we can write here 5m by 2 in this one. We can say 5m by 2 plus 240 equal to 400. So you can say, sir, 5m by 2 equal to 160. From here we can write m 32 into 2. That becomes actually 64. So m becomes 64 gram. Okay. I hope this thing is clear now. Yes. Anyone having any problem in this one? Sir, I have a doubt. If ice is converted into gas in given question, how should we do? Is there a shortcut? No shortcut. You can do like this. Okay, ice to water, water to steam. Okay, this process is same. For the shortcut, you can just minimize those steps, but process will remain same. Okay, ice will be going to water, water will be going to steam. Okay, you have to follow all the, okay, you have to follow all the steps. You are missing any single step, calculation, okay, somewhere mistake will be there. Okay, so we have to follow all the steps. Okay, clear? Means shortcut is not there. Only thing you can do the calculation fast. Okay, calculation we can do fast. Process will remain as it is. So now we are going to write next thing here. Okay, right? Concept of mixture. Right? Concept of mixture. concept of mixture, okay, right, based on energy conservation, okay, concept of mixture based on energy conservation. What will happen in the mixture? We are going to mix one material or one substance which will be at the low temperature and one will be at the high temperature. So high and low temperature we are going to mix, means someone will be having more energy and someone will be having lesser energy, and when they have to come to the equilibrium, okay, means their temperature is going to be same, means ultimately energy we have to equalize, and to equalize the energy means someone will release the energy and other is going to absorb the energy. So release energy should be equal to the absorb energy all the time in the mixture. Release energy, someone which is at the higher energy level, higher temperature, okay, which is having more energy will be releasing the energy, and someone, okay, which is at the lower energy, okay, will be taking the energy, and then they will equalize the things. So we can say heat released equal to heat absorbed, heat released, okay, heat released equal to heat absorbed, okay. Now from outside we are not taking any energy, that's why I'm saying energy conserved, okay, only they are balancing the energy of each other. From outside I am not going to supply any energy, or this energy is not going outside also, okay. No energy is released into surrounding and no energy is coming from outside, so energy will remain conserved, okay. Only they are exchanging the energy, they are balancing the energy of each other, they are exchanging the energy. From outside there is no transfer of, okay, there is no exchange of energy with the surrounding. Clear? So energy conservation, energy release equal to energy absorbed. One is at the low temperature, one is at the higher temperature. So you can say the temperature of the mixture will be between low and high. Temperature of the mixture can be more than higher temperature. Temperature of the mixture can be more than higher temperature. Temperature of the mixture can be more than higher temperature. Yes? No. Temperature of the mixture can be low than lower temperature. Low than lower temperature. Low than lower temperature. Yes? Low than lower temperature also not possible. It's always in the between, okay, this will be there, and here we can say it will be more than this and lesser than this. In some conditions it will be equal, we will see, okay. In a lot of conditions it can be equal also, okay. Temperature of the mixture can be equal to the higher temperature and temperature of the mixture can be equal to the lower temperature. Numerically of course we will see, okay, numerically we will see these things, okay. Now you will be saying, sir, okay, tell practically how it is possible, okay. Practically this thing is possible or not possible, okay. So listen, if I say that a huge block of ice, this is a huge block of ice here, okay, at 0 degrees Celsius. So huge block of ice at 0 degrees Celsius, it can be equal. You have to remember, okay. Lot of people don't remember this equal word, okay. They will always remember like this, it will be between, and whenever they ask the statement or a certain type question, the temperature of the mixture can be equal to the high temperature or temperature of the mixture can be equal to the low temperature, people do mistake in that one, okay. It can be equal, okay. It can be equal. First you remember, numerically I will explain in lot of questions. Now I'm explaining experimentally or theoretically. You can say ice 0 degrees Celsius, okay. In this ice, if I drop 2-3 drops of water, okay, 2-3 drops of water at 100 degrees Celsius, 2-3 drops of water, okay, what will happen finally? If I drop 2-3 drops of water, finally what will happen? Yes? Finally, what will happen if I drop 2-3 drops? You will say, sir, with these 2-3 drops, okay, here some ice will melt, okay, and this 100 degrees Celsius water also will come to the 0 degree Celsius water. Ice will melt, so you will be having some water, okay, some water and some ice. Some ice will melt, but okay, and ice will melt, and the temperature will be basically 0 degree Celsius. So we can say some ice will be there, some water will be there, some ice and some water will be there. Okay, but temperature will be 0 degrees Celsius only. temperature of the mixture, because whenever ice and water both are there, if ice and water both are there, ice plus water, then always temperature is what? 0 degrees Celsius. If temperature and ice both can be at what temperature under normal condition? Ice and water both can be at the 0 degrees Celsius at the normal condition. So if ice and water both are the 0 degrees Celsius, it means in this case, temperature of the mixture, I was mixing 100 degrees Celsius and 0 degrees Celsius. In this case, temperature of the mixture is equal to the lower temperature. Proved? In this case, temperature of the mixture equal to the lower temperature. Possible or not possible? Possible, na? Yes. And if I say, suppose in this room there are the huge steam at the 100 degrees Celsius, huge steam is there, okay, and this steam, if I fuse, okay, if I just infuse or if I just drop 2-3 drops of water at 0 degrees Celsius, 100 gram steam is there, full steam in this room. If I just drop 0 degrees Celsius water, what will happen? You can say, sir, this 0 degrees Celsius water, okay, will be going to the 100 degrees Celsius water, and at the same time some of the steam will condense. Some, okay, some part one droplets will condensed. Okay, so some water will be there. Some water will be there. Some steam will condense. So whenever this steam will condense, this after condensation, this steam will come to the 0 degrees Celsius, 10 degrees Celsius, 50 degrees Celsius, or 100 degrees Celsius. Because in this room there is a huge steam. Huge steam is there. So after condensation, this much steam suppose condensed, of course this will come at the 100 degree Celsius. After condensation, it will be coming at the 100 degree Celsius. And if coming at the 100 degree Celsius, then finally in the mixture will be having steam plus water, both at the 100 degree Celsius. Both at the 100 degree Celsius. Means here we can say temperature of the mixture equal to the higher temperature. Means if higher, okay, quantity with higher temperature is more huge, if this quantity is huge, then temperature can be equal to the higher, and if this quantity is huge, temperature can be the, okay, equal to lower temperature. So equal is also possible. Clear? Are done? Yes, equal possible na? Okay, so now I'm going to tell, okay, mixture is basically your liquid mixture, ice water mixture, water steam mixture. So many mixtures are there. So which mixture I can complete today? First of all, liquid can we complete first, because liquid is much easier. So suppose if I say here liquid, okay, this is the liquid 1, this is the liquid 2, this is only for liquid, okay, not valid for ice mixture, okay, only for liquid, okay. M1 S1 theta 1, and this one is having mass M2 and S2 and theta 2, okay. If I mix here, then for the mixture temperature actually becomes theta M. So now I will write always this side, okay, here I will write lower energy, lower temperature, okay, this side lower temperature, and this side I will write always higher temperature. Now this is my convention, okay, my class, my convention, my method. You, if you want, you can follow. Otherwise, so many methods are there for the mixture, okay. But for me, I will write this side always lower, okay, this side lower energy, and right side I will write higher energy, okay. Left side lower, right side higher energy, okay. So follow this thing. Otherwise, okay, you will say, sir, answer not coming. If you are not putting exactly same way you have to write, okay, you will never, not a single question you are going to do the mistake. And if you don't follow, somewhere mistake may happen, okay. So we can say this will absorb and this will release, because this is at the lower temperature. How much energy it will absorb? M1 S1 delta theta. So we can say theta M minus theta 1, because you know theta M will be more than theta 1, okay. Or even though it will be the bigger, okay, middle temperature. This side we can say this temperature is more, so it will release M2 S2, and here we can write in this one theta 2 minus theta M. Theta of the mixture we have to find. Okay, again this is only for the liquid, okay. So we can multiply M1 S1 theta M minus M1 S1 theta 1 equal to, we can say, M2 S2 theta 2 minus M2 S2 theta M, okay. Then theta M I can take, because mixture I have to find one side, so theta M one side, so here becomes M1 S1 plus M2 S2 equal to, we can write here m1 s1 theta 1 plus m2 s2 theta 2. Okay, I hope this part is clear. So we can say theta m finally equal to, we can say m1 s1 theta 1 plus m2 s2 theta 2 divided by, we can say m1 s1 plus m2 s2. But use this one only for which one? Use for which one? I will say use for only liquid. I will not suggest to use for others. Some cases answer may come for other also. For ice water also answer may come. Okay, answer may come for ice water also, but I will say for the liquid only. Okay, for those ice water, water steam, ice steam, I will tell different methods. Okay, this one we will use only for the liquid, energy release, energy absorb, and this is the formula. And this formula also I am not going to use anywhere. Okay, this formula also I am not going to use at all. Okay, I will never be using this one. Only thing, sometimes they ask the formula. If they are asking the formula, we can keep, okay, in the mind. If anywhere they are asking, we can tell this thing. Yes. Okay. Can I tell the next question here? Next one. Okay, next question. So this formula you remember, m1 s1 theta 1 plus m2 s2 theta 2 by m1 s1 plus m2 s2. Okay. So they are saying equal amount of two liquid A bracket 20 degrees Celsius and B 50 degrees Celsius are mixed if temperature, sometimes they will ask temperature of mixture and sometimes they will give you temperature of mixture. Like in this question I am giving temperature of the mixture. So if temperature of mixture is 32 degrees Celsius, find ratio of specific heat. Okay, ratio of specific heat. So we can say, sir, this side A lower temperature, this side B higher temperature, this is at 20 degrees Celsius, this one at the 50 degrees Celsius, and we can say here mixture, and mixture is basically at what temperature here? 32 degrees Celsius. This one is your M, this is also M. Okay, equal amount is given. So we can say this will absorb the energy and this will release the energy. So how much energy it will absorb? M S A delta theta, we can say 32 minus 12. Okay, 12. This side we can write M SB, and what is the temperature here? 50 minus 32, that is the 18. Here energy absorb and here energy release. Okay, then we can say mm will be cancelled here, so we can write SA by SB. Okay, SA by SB. Using 6 I can cancel, so here 2 and here 3. So finally it becomes 3 by 2. That is your SA by SB. Okay, SA by SB becomes 3 by 2. Yes, any problem here? Clear this question? Anyone, any problem? Okay, can we take one more question? One more question. Okay, so during winter time, basically, you know that we have to use geyser, and in the geyser, now we have the automatic system that automatically we can move the lever this side, okay, for our desired temperature, okay, hot water. But earlier, what was there? We were having one connection in which hot water was coming, and we were having one tap in which cold water was coming, and then manually we need to mix. Manually mixing was required. Okay, that this much hot, and then we keep on checking the okay like this. Okay, okay, now it is okay. This was the system. It's still okay. We are using the okay. Some of you might have used that system. Okay, so basically, I can say that this is the cold tap. Okay, from the cold tap, this is at the 10 degrees Celsius, or I guess suppose 20 degrees Celsius from this. Okay. Or okay, someone who's no, sir, I will take chill water. Okay, chill water means we can say this is the your 5 degrees Celsius. Okay, quite chill. If you want 0, you can take 0 also. And this side we have cold. This was the cold tap. Okay, cold tap. And this side we have hot tap. Okay, hot tap. and from the hot tap we'll be getting suppose 100 degrees Celsius water. Okay. Now they will ask here in the question, find how much water should be taken from hot tap to get, how much water should be taken from hot tap to get 20 kg water at 40 degrees Celsius. Means finally I want 20 kg and means mixture I actually want, I have to mix both. I want okay 40 degrees Celsius and 20 kg total. Okay. So if I assume, because they are asking from how much you have to take from the hot. So if I assume here m kg, if I am taking here m kg, it means you can say here how much? 20 minus m 100%. Because total is the 20. If I am taking here m, then here will be 100%, 20 minus m. If I take here m, then that side will be 20 minus m 100%. Okay. Then we can say this will absorb and this will release. So how much it will absorb? We can say ms delta theta. So 20 minus m, both side waters will be cancelled. So I can put s and delta theta we can write here 40 minus 5, that will be the 35 here. And I can write here in this one m into s, and this side will be having how much? Your 60. Now ss will be cancelled. Using 5 I can say this will be the 7, and here I can say this will be the 12. So we can say 140 minus 7m equal to, you can say 12m. So 19m equal to 140. So m actually becomes 140 by 19 kg. Okay. You can take roughly 20, so it becomes almost 7 kg water we need. Almost 7 kg from hot we need. Yes, this thing is okay. And this question okay na, hot tap, cold tap, how much we have to take. If they ask from the cold tap, we can assume cold tap as m, and this side we can write 20 minus m. Okay. Now after that comes ice and water. Okay, so in the next class you will okay tell me that ice water we have to start. Ice water mixing. Liquid is over. Ice water will start. So don't attempt those questions of ice water right now. Okay, we'll do later on. Okay, next week. Ice water and all the things. Okay. Yes. Another case I'm saying that here I can take m and here I can take 20 minus m. Okay. Here m kg. So here will be the 20 minus m. Okay. Yes. Okay, so bye. We'll meet in the next class. Meanwhile, practice these questions, whatever we have done today. Okay. Yes. Bye. Okay. Your QR is coming now. Okay. Bye. Okay.